Have you ever walked into a room that was completely dark, and though you could see nothing, you felt a presence? Perhaps it was a subtle shift in the air or a feeling of weight that you could not explain, but you knew with an instinct older than language that you were not alone. We rely so heavily on our eyes. We trust the photons that bounce off objects and strike our retinas to tell us what is real and what is not. If we can see it, touch it, or hold it, we call it matter. We call it reality. When we look up at the night sky from a quiet, dark location, we see a glittering tapestry of stars, the glowing band of the Milky Way, and the faint smudges of distant galaxies. We look at that grandeur and we think, this is the universe. We imagine that the bright shining things are the main characters in the cosmic story, and that the darkness between them is merely empty stage. But what if I told you that our eyes are lying to us? What if the universe we see, the stars, the planets, the gas clouds, the dust, and even you and me, is not the ocean, but merely the foam resting on top of a vast invisible sea? What if the true shape of reality is hidden from us, passing through our bodies at this very moment, like a ghost, silent and unseen, yet holding the entire cosmos together with a gravitational grip that nothing can escape? The story of the universe is not a story of light. It is a story of shadows. For centuries, we believed that we understood the basic building blocks of existence. We cataloged the elements, we split the atom, and we mapped the subatomic zoo of protons, neutrons, and electrons. We called this baryonic matter, a fancy term for the stuff that makes up everything you have ever touched, tasted, or loved. We assumed that this baryonic matter was the sum total of creation. It was a comforting thought. It meant that we belonged, that we were made of the same fundamental substance as the rest of the cosmos. But as we began to look harder at the movements of the galaxies and the structure of the ancient light left over from the Big Bang, we found a terrifying discrepancy. The numbers did not add up. The universe was too heavy. There was more gravity pulling at the stars than could be explained by the visible matter. It was as if we were looking at a merry-go-round spinning wildly fast, so fast that the children riding it should have been flung off into the grass, yet they remained perfectly in place, held by an invisible hand. We realized, with a slow and dawning humility, that we are not the norm. We are the exception. The matter that makes up your body and the stars is a rare, exotic dust sprinkled lightly over a universe made of something else entirely. Before we dive deeper into this invisible ocean to understand the quantum nature of the ghost that haunts our cosmos, I am Walter, the explorer. I have noticed that 73% of the curious minds who join us on these journeys have not yet subscribed to our channel. If you find peace and wonder in these explorations of the unknown, please take a moment to subscribe. It helps us tremendously to keep bringing these stories to you, and it ensures that we can continue this voyage into the mysteries of the universe together. Now, let us return to the darkness. To understand the scale of what we are missing, we must look at the recipe of the cosmos. If the universe were a cake, the normal matter, the atoms, the stars, the galaxies, the gas in us, would be nothing more than a thin layer of frosting on top. Specifically, ordinary matter makes up only about 5% of the total energy and mass of the universe. 5%. That is all. Everything we have ever seen in our telescopes, every star that has ever burned, every galaxy that has ever spun, is contained within that tiny sliver. The rest is darkness. About 68% is dark energy, a mysterious force pushing the universe apart. which we will leave for another night. But the remaining 27% is something physical, something that clumps together, something that has gravity, but something that refuses to interact with light. We call it dark matter. The name is somewhat misleading. It implies that it is a black substance, like soot or coal. But if you were to hold a lump of dark matter in your hand, it would not look black. It would look like nothing at all. It would be perfectly transparent. Light would pass through it as if it were not there. It would not cast a shadow. It would not reflect a reflection. You would not feel it resting on your palm, because the electromagnetic forces that allow you to touch things, the resistance of electron clouds pushing against each other, do not exist for dark matter. It would slip through your hand, through the floor, and through the earth, falling toward the center of gravity without ever slowing down. This substance is the invisible scaffold of the universe. When we run computer simulations of how the universe evolved from the Big Bang to the present day, we see that without dark matter, nothing would make sense. In the early universe, everything was a hot, expanding soup of particles. If there were only normal matter, the radiation from the Big Bang would have smoothed everything out. Gravity would have been too weak to pull the gas together into clumps. Stars would never have ignited. Galaxies would never have formed. The universe would be a boring, featureless fog of expanding gas. But dark matter was there. Because it does not interact with light, it was not pushed around by the intense radiation of the early universe. It was able to collapse early, forming dense pockets of invisible mass. These pockets became the seeds of structure. They created deep gravitational wells that acted like cosmic drains. The normal matter, the gas that would become stars, flowed into these dark matter wells, pooling in the center and igniting to form the galaxies we see today. Every galaxy you see in a telescope is merely the glowing heart of a much larger, invisible sphere of dark matter. The Milky Way is not just a disk of stars. It is a disk of stars embedded in a massive, spherical halo of dark matter that extends far beyond the visible edges of the galaxy. We are living inside a ghost. But what is this ghost made of? This is where the story descends into the strange and beautiful world of quantum physics. For a long time, astronomers hoped that dark matter might be something simple. Maybe it was just dead stars, or wandering planets, or black holes, things made of normal matter that just happened to be dark. We called these machos, or massive compact halo objects. It was a clever name, but it turned out to be wrong. We have searched for these objects. We have watched millions of stars for years, waiting for a dark object to pass in front of them and magnify their light through gravity. We found a few, but not nearly enough to account for the missing mass. The dark matter cannot be made of protons and neutrons. If it were, it would have upset the delicate balance of nuclear reactions in the first few minutes of the universe, changing the amounts of hydrogen and helium we see today. The evidence is clear. Dark matter is something new. It is a type of particle that we have never created in a laboratory. It is a particle that does not feel the electromagnetic force. It does not feel the strong nuclear force that binds atomic nuclei together. It feels only gravity and perhaps the weak nuclear force. This realization leads us to one of the most compelling theories in modern physics, and the protagonist of our mystery, the WIMP. The acronym stands for Weakly Interacting Massive Particle. It is a playful name for a profound concept. The theory suggests that the universe is filled with heavy particles that were forged in the intense heat of the Big Bang, just like protons and neutrons. But unlike protons, these particles are shy. They barely interact with the rest of the universe. They drift through space in vast clouds, passing through stars and planets as if they were smoke. But they are not smoke. They are heavy. Imagine a rainstorm where every raindrop weighs as much as a bowling ball, but they pass right through your roof and your body without leaving a mark. That is the reality of the WIMP. If this theory is correct, then right now, at this very second, billions of dark matter particles are streaming through your body. They are coming from the sky, passing through your skin, your organs, and your bones, and exiting through the floor, continuing their journey through the earth and out the other side. You are being washed in a constant, invisible river of ancient particles that have been traveling since the dawn of time. You cannot feel them. They do not trigger your nerves. They do not disturb your atoms. They are like travelers from a parallel dimension who share our space but not our lives. The existence of such a particle would solve many riddles. It fits perfectly with our understanding of the Big Bang. If we calculate how many of these particles should have been produced in the first moments of creation, the number matches exactly the amount of dark matter we need to explain the rotation of galaxies. Physicists call this the WIMP miracle. It is a rare moment in science where two completely different lines of inquiry, the astronomy of the largest scales and the quantum physics of the smallest scales, seem to point to the exact same answer. It feels like a key sliding into a lock. But there is a catch. A key is only useful if it opens the door. And despite decades of searching, despite building the most sensitive detectors in the history of humanity, we have never caught a WIMP. We have built traps deep underground, buried in abandoned gold mines and beneath mountains, shielded from cosmic rays and radiation, waiting in the silence for a single dark matter particle to bump into an atom of xenon or germanium. We are listening for a whisper in a hurricane. We have waited for years, and the detectors remain silent. This silence is becoming loud. It is forcing us to question our assumptions. What if dark matter is not a WIMP? What if it is something even stranger? The quantum world is not limited by our imagination. There are theories that dark matter could be made of axions, particles so light that they behave more like waves than particles, washing through the universe in a quantum condensate. There are theories of sterile neutrinos, ghostlier cousins of the already ghostly neutrino. There are theories of dark photons and entire dark sectors, a whole shadow chemistry with its own dark forces and dark atoms that never interact with ours. We are standing on the edge of a vast unknown. We have realized that the house we live in has many more rooms than we thought. And we are currently locked in the broom closet, peering through the keyhole. The mystery of dark matter is not just a puzzle for scientists to solve. It is a philosophical invitation. It asks us to reconsider our place in the universe. We used to think we were the center of everything. Then we learned we orbited the sun. Then we learned the sun was one of billions. Now we learn that the very stuff we are made of, the atoms that form our bodies and the ground we walk on, is a cosmic rarity. We are the glowing embers in a dark forest. But rather than making us feel small, this should make us feel precious. We are the part of the universe that glows. We are the part that can interact, that can touch, that can feel warmth and light. The dark matter may hold the galaxy together, but it cannot form a star. It cannot form a planet. It cannot form a living cell. It is the silent, cold bedrock of reality. But we are the flower that grows from it. As we embark on this journey to understand what quantum physics tells us about this invisible substance, we must adopt a mindset of gentle curiosity. We must be willing to let go of our common sense, for the universe at the quantum scale does not obey the rules of the everyday world. We will explore the frozen depths of underground mines where scientists wait for the ghost to speak. We will travel to the early universe to see how the first clumps of darkness gathered. We will look at the collision of galaxy clusters where dark matter separates from normal matter like a soul leaving a body. And we will ask the question that has haunted humanity since we first looked up at the stars. What is out there in the dark? The answer may be stranger than we can conceive, but the search itself is a testament to the human spirit. We are creatures of light trying to understand the shadows, and in that effort, we find a connection to the infinite mystery that surrounds us. The night sky is not just a picture to be admired. It is a puzzle to be solved, and the missing pieces are not lost. They are all around us, hiding in plain sight, waiting for us to learn how to see them. As we close this first chapter of our exploration, take a moment to feel the gravity that holds you to your chair. That gravity is not just coming from the earth below you. It is the collective pull of the entire galaxy, a pull dominated by the invisible hand of dark matter. You are being held by a ghost, and that ghost has a story to tell. Imagine standing on the edge of a vast frozen lake at night. You pick up a heavy stone and slide it across the ice. It moves quickly at first, full of energy, but as it travels farther away from you, friction steals its momentum, and it slows down until it eventually comes to a gentle stop. This is how we expect the universe to work. We expect things to slow down the farther they get from the source of their energy or the source of their gravity. In our own solar system, this rule is absolute. Mercury, the closest planet to the sun, whips around its orbit at a frantic pace, desperate to keep from falling into the burning star. Neptune, lonely and distant, drifts lazily through the dark, moving with a slowness that matches its freezing isolation. This pattern, where speed decreases with distance, is the fingerprint of gravity as we understood it for centuries. It is the logic of Isaac Newton and Johannes Kepler. It is the logic that allowed us to send spacecraft to the rings of Saturn and land rovers on the dusty plains of Mars. It is a logic that feels safe, predictable, and orderly. But the universe has a way of shattering our sense of safety when we stop looking at our own backyard and start looking at the giants that dwell in the deep cosmos. To understand the ghost that haunts our reality, we must look at how galaxies spin. A galaxy is not a solid object like a plate. It is a fluid collection of billions of stars, gas clouds, and dust, all rotating around a bright, dense center. For a long time, astronomers assumed that galaxies would behave just like our solar system. They assumed that the stars near the bright center, where most of the visible mass is concentrated, would orbit quickly, and that the stars at the distant edges, far from the gravitational pull of the core, would drift slowly. It was a reasonable assumption. It was the scientific assumption. But when we finally built instruments sensitive enough to measure the speeds of those distant, lonely stars, we found something that should not be possible. The story of this discovery is one of the most important turning points in the history of human thought, and it belongs largely to an astronomer named Vera Rubin. In the 1970s, Rubin was studying the Andromeda Galaxy, our nearest large cosmic neighbor. She was measuring the rotation of the stars at the very edge of the galaxy's spiral arms. She expected to see the rotation curve drop, indicating that the outer stars were moving slowly. Instead, she found a flat line. The stars at the edge of the galaxy were moving just as fast as the stars near the center. In some cases, they were moving even faster. This was a violation of the laws of physics as we knew them. Imagine watching a merry-go-round where the children on the outer edge are spinning at thousands of miles per hour. Yet, they are not flung off into the park. They are holding on with a grip that defies explanation. According to the visible matter, the stars and gas we could see, there was simply not enough gravity to hold those fast-moving outer stars in place. They should have been flung out into the intergalactic void billions of years ago. The galaxy should have torn itself apart. This was not a small error. It was not a rounding mistake in a decimal point. The discrepancy was enormous. For the stars to move that fast and stay in orbit, the galaxy had to contain 5 times more mass than we could see. 5 times. Imagine looking at an iceberg and realizing that the tip you see above the water is not supported by ice beneath, but by a mountain of invisible stone that you cannot touch or see. Rubens' observation forced us to confront a terrifying truth. The luminous universe, the universe of light and stars that we had studied for thousands of years, is just a deceptive facade. The gravity holding the galaxies together is not coming from the stars. It is coming from something else, something invisible, something vast. We call this the missing mass problem, but that phrase is too mild. It was a crisis of reality. It meant that when we look at a galaxy like the Milky Way, we are not seeing the galaxy itself. We are seeing only its skeleton, or perhaps its nervous system, glowing faintly in the dark. The true body of the galaxy is a massive, spherical halo of dark matter that extends far beyond the visible spiral arms. This halo is not a thin mist. It is the dominant structure. The stars are merely glitter sprinkled in the center of a dense ball of invisible matter. If you could give yourself eyes that could see dark matter, the night sky would look completely different. You would not see separate galaxies separated by empty space. You would see vast interconnected mountains of dark mass with the tiny peaks of light, the galaxies, nestled in their valleys. We are living in a universe where the most important substance is one we cannot see, taste, or feel. The implications of this are profound and humbling. It means that our sun, our planet, and our bodies are made of a rare, exotic material. We are the minority. The normal state of matter in the universe is dark, cold, and invisible. We are the anomalies. This realization brings a certain kind of vertigo. It is the feeling of standing on a glass floor over an infinite abyss. We thought we were standing on solid ground, on a universe made of atoms like us. But we are actually floating in a sea of something else, something alien. And this something else is not just out there in deep space. It is right here. If the galaxy is immersed in a halo of dark matter, then dark matter is everywhere. As the Earth orbits the Sun, and the Sun orbits the galactic center, we are moving through this invisible cloud. It is passing through your room right now. It is passing through the screen you are reading this on. It is passing through your own heart. We are like fish swimming through water, completely unaware of the medium that supports us. But unlike fish, who can feel the water's resistance, we feel nothing. This is where the mystery deepens into the realm of the quantum. If dark matter has mass, enough mass to hold a galaxy together, why does it not interact with us? Why doesn't it crash into our atoms? Why doesn't it create friction? To answer this, we have to journey into the strange rules of the subatomic world. In our daily lives, we are used to things bumping into each other. If you clap your hands, the skin of your left hand hits the skin of your right hand, and they stop. You hear a sound. You feel a sting. But at the atomic level, touching is an illusion. Your hands never actually touch. The electrons orbiting the atoms in your left hand repel the electrons orbiting the atoms in your right hand via the electromagnetic force. That repulsion is what you feel as touch. But dark matter, by its very definition, does not feel the electromagnetic force. It has no electric charge. It does not have electrons to repel our electrons. It is a ghost in the truest sense of the word. A clump of dark matter, the size of a mountain, could pass right through the earth, and the earth would not even shudder. The only thing the earth would feel is a gravitational tug, a silent whisper of attraction. This ghostly nature is what makes dark matter so difficult to study. How do you catch a ghost? You cannot use a net made of atoms, because the ghost will slip through the gaps. You cannot use a camera, because the ghost reflects no light. You can only look for the footprints it leaves behind, and the footprints of dark matter are stamped all over the structure of the universe. We see its influence not just in the spinning of galaxies, but in the way light bends as it travels through the cosmos. Einstein taught us that gravity warps space and time. A massive object acts like a lens, bending the path of light that passes near it. When we look at distant clusters of galaxies, we see the light from even more distant background galaxies being distorted, smeared into arcs and rings. This is called gravitational lensing. When we calculate how much mass is needed to create these distortions, we find the same answer that Vera Rubin found. There is 5 times more mass there than we can see. The invisible hand is at work again, bending the very fabric of space, guiding the light of ancient stars. The consistency of this evidence is what gives scientists the confidence to believe in something they cannot see. It is not a guess. It is not a story we tell ourselves to fill the silence. It is a rigorous conclusion drawn from multiple independent lines of evidence, from the rotation of individual galaxies to the movement of vast galaxy clusters, from the bending of light to the patterns in the afterglow of the Big Bang. Everything points to the same thing. The universe is filled with a cold, slow-moving, invisible substance. We call it cold, dark matter. Cold, not because of its temperature in degrees, but because it moves slowly compared to the speed of light. If it moved fast, it would be hot, dark matter, and it would have washed out the structure of the universe, preventing galaxies from forming. The fact that we exist, that galaxies exist, tells us that the dark matter is cold. It is a sluggish, heavy ghost. But knowing what it is not is different from knowing what it is. We have defined it by its silence. We know it is not a proton. We know it is not an electron. We know it is not a neutrino. It is a mystery particle, a piece of the cosmic puzzle that has been lost under the couch since the beginning of time. This is where the WIMP, the weakly interacting massive particle, enters our story as the prime suspect. The WIMP is a theoretical particle that arises from our attempts to unify the forces of nature. It is a beautiful idea. It suggests that for every particle we know, there is a heavier, invisible partner. The WIMP would be heavy enough to provide the missing mass, but shy enough to avoid detection. It fits the data perfectly. It is the perfect suspect. And yet, despite its perfection on paper, the WIMP remains elusive. We have built cathedrals of science to find it, deep underground in places like the Gran Sasso Mountain in Italy or the Sanford Underground Research Facility in South Dakota. Scientists have constructed tanks of liquid xenon and germanium crystals. These detectors are the most sensitive ears humanity has ever built. They are shielded from the noise of the surface world, the cosmic rays, the radiation from rocks, the radio waves from our phones. In the profound silence of the deep earth, they wait for a single WIMP to nudge a single nucleus. It is a vigil of patience and hope. They are waiting for the universe to whisper its secret name. But so far, the detectors have heard only silence. The WIMP has not shown itself. This silence is beginning to make us nervous. It is beginning to make us wonder if we have misunderstood the ghost. Could it be that dark matter is not a particle at all? Could it be that our understanding of gravity is wrong? There are those who suggest that perhaps Newton and Einstein were not quite right, that gravity behaves differently on cosmic scales. This theory, called modified Newtonian dynamics, or MOND, suggests that there is no dark matter, only a misunderstanding of how gravity works at low accelerations. It is a seductive idea because it removes the need for invisible monsters, but it struggles to explain the other footprints, the gravitational lensing, the cosmic microwave background. The universe seems to insist on the ghost. The evidence for dark matter is stubborn and resilient. So we are left with a profound mystery. We have found the tracks of the beast. We have measured its weight. We have mapped its home. But we have never seen its face. This state of not knowing is uncomfortable for a species that prides itself on conquest and understanding. We want answers. We want to label the jar and put it on the shelf. But there is a beauty in the mystery. It reminds us that the universe is not obligated to be simple. It is not obligated to be understandable to the minds of primates who evolved on the African savanna. The universe is vast, ancient, and strange. The fact that we can understand even 5% of it is a miracle. As we stand on the precipice of this unknown, looking out into the dark halo that surrounds our galaxy, we should feel a sense of connection, not isolation. The dark matter is not a wall separating us from the cosmos. It is the glue holding us together. Without it, the sun would drift away into the void. Without it, the earth would be a lonely wanderer in the intergalactic night. The darkness is not empty. It is full. It is full of mass, full of structure, full of the silent gravity that cradles the stars. We are held in the arms of a giant we cannot see, protected by a shield we cannot touch. This invisible ocean allows for our existence. It allowed the gas to pool and form the first stars. It guided the galaxies into the cosmic web. It is the silent architect of reality. And even if we never catch a WIMP, even if the true nature of dark matter remains forever beyond the reach of our detectors, we have learned something profound about our place in the cosmos. We have learned that there is more to reality than meets the eye. We have learned to look at the darkness not as an absence of light, but as a presence of something else, something ancient, something necessary, something fundamental. The journey to understand this ghost takes us from the largest scales of the galaxy down to the smallest scales of the subatomic world. In the next chapter, we will shrink ourselves down. We will leave the spinning galaxies and the gravitational lenses behind and enter the quantum realm, a place where particles can be in two places at once, where empty space is frothing with energy, and where the answer to the dark matter riddle might be hiding in the fluctuations of the vacuum itself. We will ask if the dark matter is made of something even stranger than a WIMP? Could it be a particle that can change its identity? Could it be a particle that hides in extra dimensions? The quantum world is a wonderland of possibilities, and we are just beginning to open the door. So, as you sit here, feeling the gravity that anchors you to the earth, remember that you are feeling the tug of the mystery. You are feeling the presence of the invisible. You are an explorer in a universe that is mostly hidden, a traveler in a land of shadows. And the journey is far from over. The darkness has secrets yet to tell, and we are listening. We are always listening. To understand the true nature of the ghost, we must leave the realm of the very large, the spinning galaxies and the bending light, and descend into the realm of the very small. We must shrink ourselves down past the size of a mountain, past the size of a grain of sand, past the size of a single atom, until we reach the fundamental fabric of reality itself. Here, in the quantum world, the rules of common sense dissolve. Here, particles are not solid little balls of matter. They are ripples in invisible fields, vibrations in a cosmic ocean that pervades every centimeter of space. For a long time, we thought of empty space as truly empty, a void where nothing existed. But quantum physics has taught us that there is no such thing as emptiness. The vacuum of space is alive. It is seething with energy, bubbling with virtual particles popping in and out of existence, and humming with the vibrations of fundamental fields. It is in this quantum choir that the secret of dark matter may be hiding. If the WIMP, the heavy, shy particle we discussed before, is the standard suspect, the detective's favorite theory, then the quantum world offers us a stranger, more elegant alternative. Imagine for a moment that the universe is a vast, calm lake. The particles we know, electrons, quarks, photons, are like boats floating on the surface or waves crashing on the shore. But what if dark matter is not a boat? What if it is the water itself? This brings us to one of the most fascinating candidates for dark matter, the axion. The story of the axion begins not with a search for dark matter, but with a flaw in our understanding of the neutron. In the 1970s, physicists were troubled by a puzzle called the strong CP problem. It is a technical name for a simple mystery. The neutron, a neutral particle, should theoretically have a slight separation of positive and negative charge within it. It should respond to electric fields. But nature is stubborn. Every measurement showed the neutron to be perfectly, inexplicably neutral. It was as if a spinning top that should be wobbling was spinning perfectly upright, forever. To fix this, physicists proposed a new field, a cleaning mechanism that would wipe away this wobble. This field would naturally produce a particle. They named it the axion, after a brand of laundry detergent popular at the time, because it cleaned up the problem with a strong nuclear force. But soon they realized this cleaner particle might be doing much more than just fixing a math problem. If axions exist, they would be incredibly light, billions of times lighter than an electron. They would be so light that they would barely act like particles at all. Instead, they would behave like waves. They would not clump together into hard little spheres. They would overlap and flow, filling the universe like a super cold, ghostly fluid. This axion fluid would have mass and therefore gravity, but it would not interact with light. It would be cold, dark matter. If this theory is true, then we are not just swimming through a sea of dark particles. We are submerged in a quantum ocean of axions. They are everywhere. Trillions of them could fit inside a sugar cube. They are passing through your eyes right now, spectral waves of energy that leave no trace. Searching for axions requires a completely different approach than searching for WIMPs. You cannot wait for an axion to hit an atom because it is too light to make a splash. Instead, you have to trick it into revealing itself. The theory predicts that in the presence of a very strong magnetic field, an axion can spontaneously convert into a photon, a particle of light. It is a magical transformation, matter turning into light under the influence of magnetism. To catch this magic, scientists have built machines called haloscopes. The most famous of these is the ADMX experiment, the Axion dark matter experiment. It sits deep underground, a gold-plated copper cylinder cooled to near absolute zero, surrounded by a superconducting magnet. It is essentially a high-tech radio, tuning through the frequencies of the cosmos, listening for a faint, pure tone that would signal an axion turning into a photon. It is a quiet, lonely vigil. The scientists turn the dial, frequency by frequency, listening to the static of the universe, hoping to hear the single, clear note of the dark matter ghost. They have been listening for years. They have heard nothing yet. But the radio dial is huge, and they have only scanned a small fraction of the stations. The axion could still be out there, singing its silent song, waiting for us to tune in. But the axion is not the only ghost in the quantum machine. There is another possibility, one that arises from a family of particles we already know exists, the neutrinos. Neutrinos are already the ghosts of the Standard Model. They are produced in the nuclear fires of the sun and in the explosions of dying stars. They are so elusive that billions of them pass through your thumb every second without touching a single atom. To a neutrino, the Earth is as transparent as a pane of glass, but we can detect them. Occasionally, very rarely, a neutrino will strike an atom of water or chlorine and create a flash of light. We have built massive detectors like the Super Kamiokande in Japan, a cathedral-sized tank of pure water buried under a mountain, to catch these rare flashes. However, standard neutrinos are too light and too hot, moving too fast, to be dark matter. They would not clump together to form the gravitational halos that hold galaxies together. But quantum theory allows for a cousin, a sibling, that is even more antisocial than the neutrino we know. We call it the sterile neutrino. In the world of particle physics, handedness matters. All the neutrinos we have ever observed are left-handed, meaning they spin in a specific way relative to their motion. Physics loves symmetry, so we naturally ask, where are the right-handed neutrinos? We have never seen one. The theory suggests that perhaps right-handed neutrinos do exist, but they are sterile. They do not feel the weak nuclear force. They do not feel the electromagnetic force. They feel only gravity. If sterile neutrinos exist, they would be heavier than their left-handed cousins. They would be massive enough to be cold, dark matter. They would have been produced in the Big Bang and would now be drifting through the cosmos, forming the invisible scaffolding of the galaxies. Because they are sterile, they would be almost impossible to detect directly. They would never interact with a water tank or a block of germanium. But they might have one weakness. According to quantum mechanics, a heavy sterile neutrino could, very rarely, decay into a lighter standard neutrino and a photon of X-ray light. This gives us a clue to look for. Astronomers have pointed X-ray telescopes at distant clusters of galaxies, looking for a specific, faint spike of X-ray light that cannot be explained by atomic transitions. In 2014, a ripple of excitement went through the scientific community. A faint X-ray signal at an energy of 3.5 kiloelectronvolts was detected coming from the Perseus cluster and the Andromeda galaxy. It was a whisper in the X-ray data. Could this be the dying breath of sterile neutrinos? The debate rages on. Some studies see it, others do not. It is a ghost signal from a ghost particle. The search for dark matter in the quantum realm is a lesson in humility. It forces us to confront the fact that our senses are incredibly limited. We evolved to see light in a very narrow spectrum, the colors of the rainbow, because that is the light our sun emits most strongly. We evolved to feel matter that interacts electromagnetically, because that is what we are made of. But the universe is under no obligation to conform to our sensory limitations. There could be, and likely are, entire sectors of reality, entire families of particles and forces that are completely invisible to us. Physicists call this the dark sector. It is possible that dark matter is not just one simple particle, like a WIMP or an axion. It could be as complex as visible matter. There could be dark atoms made of dark protons and dark electrons, bound together by dark photons. There could be dark stars that shine with dark light we cannot see. There could be dark planets orbiting those dark stars. There could be complex dark chemistry happening right now in the center of our galaxy, a shadow mirror of our own world. This idea of a dark sector is speculative, but it is not science fiction. It is a logical extension of what we see in our own light sector. Nature tends to be complex. Why should the dark side of the universe be simple? Imagine a civilization of blind creatures living in a cave. They can hear and touch, but they cannot see. They might build a complete science of sound and texture. They might map their cave perfectly, but they would be completely unaware of the light that floods the entrance of their cave or the colors of the flowers growing outside. We are those blind creatures. We have mastered the science of light and atoms. We have mapped our cave. But we are just beginning to realize that there is a whole world of darkness outside our perception, a world that outweighs our own 5-to-1. The implications of quantum dark matter extend to the very stability of the universe. If dark matter is made of axions or sterile neutrinos, it affects how the universe expands and how it will end. It affects the formation of the first stars and the evolution of the first black holes. It is the hidden hand that sculpts the cosmos. When we look at the cosmic microwave background, the afterglow of the Big Bang, we see the fingerprints of this sculpting. We see subtle fluctuations in temperature that correspond to the density of dark matter in the infant universe. These fluctuations are the seeds from which all structure grew. Without the quantum properties of dark matter, the universe would be a very different place. It might be lifeless. As we ponder these invisible particles, we must also consider the concept of supersymmetry. For decades, this was the leading theory in particle physics. It proposed that every particle in the Standard Model, the quarks, leptons, and bosons, has a heavier superpartner. The electron has the selectron. The photon has the photino, and so on. The lightest of these superpartners would be stable, heavy, and invisible, the perfect WIMP. It was a beautiful theory that solved many mathematical problems. Scientists hoped that the Large Hadron Collider, the giant atom smasher in Geneva, would create these superparticles. They smashed protons together at nearly the speed of light, recreating the energies of the Big Bang, hoping to see a superparticle emerge from the debris. They found the Higgs boson, the God particle, which gives mass to other particles. It was a monumental triumph. But they found no superparticles, no selectrons, no photinos. Supersymmetry, the beautiful theory, is under siege. Nature, it seems, might not be supersymmetric. This has pushed the search back toward the axion and the dark sector. It has reminded us that Beauty in mathematics does not always equal truth in nature. So, where does this leave us? We are standing in a room full of invisible elephants. We can feel the floors shaking when they walk. We can see the furniture being pushed aside, but we cannot see the elephants. We have built traps for wimps, radios for axions, and telescopes for sterile neutrinos. We are trying every trick we know to make the invisible visible. It is a pursuit that requires infinite patience. It is a multi-generational project. The physicists who built the first dark matter detectors have grown old. Their students are now leading the experiments. Their students are designing the next generation of machines. It is a cathedral of curiosity, built stone by stone, year by year. There is a profound peace in this long search. It reminds us that we are part of a continuous journey of discovery. We are not expected to solve the riddle of the universe in a single lifetime. We are only asked to add our piece to the puzzle. Whether dark matter turns out to be a WIMP, an axion, a sterile neutrino, or something we have not yet imagined, the answer will change our understanding of reality forever. It will be a revolution as great as the discovery that the Earth orbits the Sun. It will rewrite the textbooks. It will open new doors to new physics. In the next chapter, we will step back from the microscopic world of quantum fields and look at the macroscopic history of the universe. We will travel back in time to the cosmic dawn, the era when the first stars ignited in the darkness. We will see how dark matter acted as the midwife for these first suns, gathering the primordial gas into its gravitational embrace. We will explore the cosmic web, the vast filamentary structure of dark matter that connects the galaxies across billions of light years. We will see that the universe is not a random scattering of objects, but a structured, organized web of light and shadow, built by the ghost we are trying to find. For now, let the mystery of the axion and the sterile neutrino settle in your mind. Think of the billions of invisible waves passing through you. You are transparent to the dark universe. You are a ghost to them, just as they are ghosts to you. We exist in parallel, occupying the same space, separated only by the nature of our forces. It is a humbling thought, but also a beautiful one. The universe is full. It is rich. It is crowded with existence. We are never truly alone in the dark. To understand the true power of the ghost that haunts our universe, we must travel back to a time before the stars. We must go back to an era of profound silence and absolute darkness, a time astronomers call the cosmic dark ages. Imagine a universe without a single point of light. No suns, no galaxies, no planets, no moons. Just an endless, expanding fog of hydrogen and helium gas drifting in the void. This was the state of our cosmos about 380,000 years after the Big Bang. The initial fires of creation had cooled and faded, leaving behind a universe that was smooth, uniform, and cold. If you had been there, floating in that primordial abyss, you would have seen nothing but blackness in every direction. It was a stillness that lasted for 100 million years. 100 million years of night. But in that darkness, something was moving. The ghost was at work. While the ordinary matter, the gas that would one day make up your body and the stars, was hot and pressurized, pushing outwards against gravity, the dark matter was cold and patient. Because it does not interact with light, it did not feel the pressure of the radiation left over from the Big Bang. It was immune to the heat. And so, while the normal gas was still expanding, the dark matter began to collapse. It began to fall in on itself, drawn together by its own gravity. Slowly, inevitably, The invisible particles clustered together. They formed dense knots in the fabric of space. They formed long, invisible filaments stretching across millions of light years. They built a skeleton in the dark. This is the most important structure in the universe, and you have never seen it with your own eyes. We call it the cosmic web. If you could zoom out and look at the universe from a God's eye view, stripping away the blinding light of the stars, you would see a vast, intricate spider web made of dark matter. It looks like the neural network of a giant brain, or the mycelium of a fungus spreading through soil. Thick strands of dark matter connect massive, dense nodes, and between these filaments lie enormous, empty voids, regions of space where almost nothing exists. This web is the scaffolding of reality. It is the invisible architecture that determined where every galaxy, every star, and every planet would eventually be born. During the cosmic dark ages, this web was the only thing with structure. The ordinary gas was just a smooth mist, unaware of the shape it was destined to take. But gravity is a relentless engine. As the dark matter filaments grew heavier and denser, they began to pull on the ordinary gas. The hydrogen atoms, floating aimlessly in the void, felt the tug of the ghost. They began to flow. Rivers of gas, millions of light years long, streamed into the gravitational valleys created by the dark matter. They poured into the knots where the filaments intersected. The dark matter acted as a cosmic womb, gathering the raw materials of creation and holding them tight against the expansion of the universe. Without this dark matter trap, the first stars would never have ignited. The gas would have been too thin, too hot, and too spread out to collapse on its own. It needed the extra weight, the extra gravity of the ghost to squeeze it down. Inside these dark matter halos, the pressure mounted. The gas grew denser and hotter. The atoms slammed into each other with increasing violence. And then, in the deep silence of the dark ages, a spark was lit. Nuclear fusion ignited. The first star in the history of the universe flickered into existence. It was a monster hundreds of times more massive than our sun, burning with a furious blue-white light. It was followed by another and another, until the nodes of the cosmic web began to glow. The dark ages were over. The era of starlight had begun. We owe our existence to this invisible midwife. Every photon of light that hits your eye, every atom of carbon in your DNA, exists because dark matter gathered the gas together long ago. We are living in the lighted windows of a house built by a ghost. But the story of the cosmic web is not just ancient history. It is happening right now. The web is still there, and it is still guiding the motion of the universe. When we look at the distribution of galaxies today, we see that they are not scattered randomly like salt on a table. They are strung out along the filaments of the dark matter web like pearls on a necklace. This alignment tells us something profound about the nature of the dark matter particle itself. Remember the WIMP, the cold, heavy particle we discussed? The shape of the cosmic web confirms that dark matter must be cold. If dark matter were hot, if it were made of light, fast-moving particles like neutrinos, they would have zipped around the early universe at nearly the speed of light. They would have smoothed out the knots and erased the filaments. The web would be blurry, like a photograph taken with a shaking hand. But the web we see is sharp. The filaments are defined. The galaxies are clustered tightly. This sharpness is the fingerprint of a slow, heavy ghost. It tells us that whatever dark matter is made of, it moves sluggishly. It clumps. It builds. But there is a mystery within the web, a problem that keeps astronomers awake at night. We call it the cusp core problem. When we run our computer simulations using cold dark matter, the math predicts that every galaxy should have a steep, sharp spike of dark matter right in its center, a cusp. The density should shoot up dramatically as you get closer to the core. But when we observe real galaxies, especially small dwarf galaxies, we often see a flat, constant density of dark matter in the center, a core. It is as if something has stirred up the center and smoothed out the spike. The simulation predicts a mountain. The telescope sees a plateau. This discrepancy might seem small, but in physics, the small cracks are where the light gets in. It suggests that our simple picture of cold, non-interacting dark matter might be too simple. Perhaps the dark matter particles do interact with each other. Perhaps they bounce off one another like billiard balls, creating a pressure that pushes back against gravity and smooths out the core. This theory is called self-interacting dark matter. It paints a picture of a dark sector that is alive with its own forces. Imagine a hidden world where dark matter particles are not just ghosts passing in the night, but physical objects that collide, scatter, and maybe even form dark atoms or dark molecules. If this is true, the centers of galaxies are chaotic, violent places in the dark sector, teeming with invisible collisions that shape the visible world. Another possibility is that the ordinary matter, the stars and gas, is pushing back. When massive stars explode as supernovas, they drive powerful winds of gas out of the galaxy's center. This sudden removal of mass changes the gravitational field. The dark matter, feeling the loss of gravity, expands outward, turning the sharp cusp into a smooth core. This would mean that the baryonic matter, the stuff we are made of, is not just a passive passenger. We are fighting back. The exploding stars are reshaping the dark matter halos that gave them birth. It is a cosmic dance of feedback, a conversation between the light and the dark. The cosmic web also holds the secret to the ultimate fate of the universe. The web is fighting a war against the expansion of space. Gravity is trying to pull everything together to make the knots tighter and the filaments stronger. Dark energy is trying to rip everything apart, stretching the voids and pushing the clusters away from each other. For billions of years, gravity was winning. The web was growing. But about 5 billion years ago, the tide turned. Dark energy took over. The universe began to accelerate. Today, we see that the largest structures in the web are beginning to freeze in place. The voids are growing larger. The filaments are stretching thin. The universe is being pulled apart by the nothingness itself. In the far future, billions of years from now, the cosmic web will dissolve. The galaxies that are not already bound together in tight clusters will be carried away from each other faster than the speed of light. The sky will darken, the web will tear. But for now, we live in the golden age of structure. We live in the era where the web is vibrant and strong. We can map it by looking at how it bends the light of distant galaxies. We can see its shadow in the cosmic microwave background. We are the spiders who have become aware of the web. There is a deep beauty in the idea of the cosmic web. It connects us to everything else. The Milky Way is not an island. It is a node in a vast network. We are connected by invisible bridges of dark matter to our neighbor Andromeda, and to the Virgo cluster, and to the great attractor beyond. We are part of a continuous structure that spans the entire visible universe. It reminds us that separation is an illusion. On the scale of the cosmos, everything is touching. Everything is woven together. As we visualize this web, let us return to the quantum mystery. How can a tiny subatomic particle, whether a WIMP, an axion, or something else, build a structure that is billions of light years across? It is a testament to the power of numbers. A single snowflake is fragile and small, but enough snowflakes can form a glacier that carves mountains. A single dark matter particle is a ghost, but 10 to the power of 80 dark matter particles can build a universe. The micro sculpts the macro. The invisible shapes the visible. This brings us to a humbling realization about our own bodies. The atoms that make up your hands and your eyes were cooked in the hearts of stars, but those stars were cooked in the wombs of dark matter. You are, in a very real sense, a child of the darkness. The iron in your blood was forged in a supernova, but the supernova exploded inside a dark matter halo. The carbon in your DNA was assembled in a planetary nebula, but that nebula drifted in a galaxy held together by a ghost. We are the visible expressions of an invisible desire, the desire of matter to be together, to clump, to organize, to be complex. In the next chapter, we will explore the most extreme environments in the cosmic web, the places where dark matter and ordinary matter collide with violence and fury. We will look at the bullet cluster, a crime scene in the cosmos where two massive clusters of galaxies smashed into each other. We will see how this collision separated the dark matter from the gas, providing the most direct proof we have ever found that the ghost is real. We will act as forensic detectives, examining the debris of a cosmic car crash to find the invisible driver. We will also ask if dark matter can form black holes. Could the supermassive monsters at the centers of galaxies be made not of collapsed stars, but of pure, concentrated dark matter? The universe is a place of violent beauty, and the ghost is always there, watching, holding, and shaping. As you look up at the night sky, try to see the spaces between the stars not as empty, but as the fullness of the web. You are looking at the filaments of the giant. You are looking at the structure that holds you. To understand the true nature of the ghost that haunts our universe, we must turn our gaze to a crime scene. We must look at a place in the cosmos where a violent accident has occurred, a collision so colossal that it ripped the soul of a galaxy cluster right out of its body. In the deep universe, in the direction of the constellation Carina, lies an object catalogued as 1E0657-56. Astronomers call it the bullet cluster. It is not a single object, but the aftermath of a titanic crash between two enormous clusters of galaxies. Imagine two swarms of bees, each swarm containing thousands of bees, flying towards each other at incredible speeds. If the bees were made of normal matter, like billiard balls, they would smash into each other, scatter, and stop. But galaxies are mostly empty space. When the two clusters met, the stars, the bees, passed right through the gaps between each other, missing one another entirely. The stars kept flying, largely unaffected by the violence. But the space between the stars was not empty. It was filled with the hot, thin gas we discussed in the last chapter, the intracluster medium. This gas is made of protons and electrons, and it carries an electric charge. When the two clouds of gas collided, they did not pass through each other. They slammed together with the force of 1 billion atomic bombs. The friction was unimaginable. The gas heated up to 100 million degrees, glowing brightly in X-rays, and dragged to a halt in the center of the collision. It got stuck, like a car hitting a wall of mud. This is where the story gets strange. If the universe were made only of the matter we can see, then all the mass, and therefore all the gravity, should be stuck in that central pile of hot, glowing gas. That is where the protons are. That is where the electrons are. That is where the stuff is. However, when we looked at the bullet cluster with our gravitational telescopes, observing how it bent the light from background galaxies, we found something impossible. The gravity was not where the gas was. The gravity was not in the center. The gravity had kept going. It had passed right through the crash site, just like the stars, and was now located on either side of the hot gas pile. The mass of the cluster had separated from the matter of the cluster. It was as if you were in a car crash, and while your car crumpled and stopped, your shadow detached itself from the pavement and kept driving down the highway. This observation is the single most significant piece of evidence for the existence of dark matter. It proves that the stuff holding the cluster together is not the gas. It is not the stars. It is a ghost that does not feel friction. It does not feel the electromagnetic force. It simply flows. Before we delve deeper into what this separation tells us about the particle nature of the ghost, I am Walter, the explorer. I must gently remind you that 73% of the wonderful people traveling with us on this journey have not yet subscribed. If you are finding value in this quiet exploration of the cosmos, if these stories help you feel a little more connected to the vastness above, please consider subscribing. It helps our community grow and ensures we can keep asking these profound questions together. The bullet cluster tells us that dark matter is real. It is not just a misunderstanding of gravity. If gravity were just different on large scales, it would still point back to the gas, because the gas is the bulk of the visible matter. But the gravity points to the empty space where the dark matter has moved. This separation puts a strict limit on what dark matter can be. It tells us that dark matter is collisionless. It does not interact with itself. When the two dark matter halos crashed, the particles did not bounce off each other. They did not heat up. They did not slow down. They passed through each other like two ghosts walking through the same hallway. This rules out many theories that suggest dark matter is made of hidden normal objects like dim stars or rocks. If it were rocks, they would have smashed. If it were gas, it would have heated. It must be something that transcends the friction of the physical world. But the bullet cluster is just one crime scene. The universe is full of them. We have found other colliding clusters, the train wreck cluster, the musket ball cluster, and they all show the same ghostly separation. The universe is consistent. The ghost is always there, and it always behaves with the same aloof indifference to the violence of the ordinary world. This brings us back to the question of what, exactly, this ghost is. We have looked at WIMPs, and we have looked at axions, but there is another possibility, one that is perhaps the most terrifying and poetic of all. What if dark matter is not a particle? What if it is a memory of the Big Bang itself, frozen in the form of black holes? We usually think of black holes as the corpses of dead stars. A massive star burns its fuel, collapses under its own weight, and tears a hole in the fabric of space-time. These are stellar mass black holes. But Stephen Hawking and other physicists proposed a different origin. In the very first fraction of a second after the Big Bang, the universe was not smooth. It was a chaotic, boiling foam of energy. Some regions were slightly denser than others. If a region was dense enough, it could have collapsed directly into a black hole, without ever becoming a star first. These are called primordial black holes. They are ancient. They are older than the first atom. They are the original inhabitants of the cosmos. If these primordial black holes exist, they could be the dark matter. Think about it. Black holes have mass, they have gravity, but they emit no light. They are, by definition, dark. If the universe is filled with billions of these ancient holes, they would act exactly like cold, dark matter. They would clump together. They would form halos. They would hold galaxies together. And they would pass through each other without colliding, just like the ghosts in the bullet cluster. A black hole is a very small target. Two black holes flying past each other in deep space would almost never hit. They would simply swing past, guided by gravity. But how big are these primordial ghosts? This is where the theory gets wild. They could be any size. They could be as massive as 1,000 suns, or they could be as small as a single atom. Imagine a black hole the size of a proton, but with the mass of a mountain. It would be invisible to the eye, but if it passed through the earth, you would feel a sudden, sharp jolt of gravity. It would pass through rock as easily as a bullet through fog. For a long time, scientists thought this was unlikely. We have ruled out certain sizes. If they were too big, we would see them bending light everywhere. If they were too small, they would have evaporated by now due to Hawking radiation. But there is a window, an asteroid mass window, where they could still be hiding. Imagine the universe filled with countless black holes, each the mass of an asteroid, but the size of a single atom. They would be everywhere, drifting through the solar system, drifting through your room, undetectable, except for their gravity. Recent discoveries have brought this theory back from the dead, when the LIGO Observatory detected the gravitational waves from merging black holes. The masses were surprisingly large, 30, 40, 50 times the mass of the Sun. This was heavier than we expected for normal stellar black holes. Some physicists asked, could these be primordial? Could we be hearing the collisions of ancient monsters that were born in the Big Bang? If this is true, then dark matter is not a new exotic particle. It is just gravity, folded in on itself. It is the universe hiding its mass in pockets of pure darkness. It is a beautiful, elegant solution. We do not need new physics. We just need to accept that the universe is Swiss cheese, filled with holes. However, there is a problem. If dark matter is made of black holes, they should be messy eaters. As they drift through the galaxy, they should occasionally swallow gas or dust. As the gas falls in, it should heat up and emit X-rays. We should see the sky sparkling with the faint, dying screams of matter falling into these tiny holes. We have looked, and the sky is too quiet. This silence pushes us away from the black hole theory, back towards the particle theories. But the door is not closed. Perhaps the black holes are there, but they are starving. Perhaps they are in the empty voids, where there is no gas to eat. The mystery remains. To solve this, we are turning to a technique called microlensing. We are staring at millions of stars in the neighboring Andromeda galaxy and the Magellanic Clouds. We are waiting for a dark object, a black hole, to pass exactly in front of a star. If it does, the black hole's gravity will act like a magnifying glass, causing the star to brighten for a few days or weeks. If we see enough of these twinkling events, we will know the black holes are there. We have seen a few, but not enough to account for all the dark matter. It seems likely that primordial black holes make up only a fraction of the dark sector. Maybe 1%, maybe 10%. The rest must be something else. This leads us to a profound realization about the complexity of the dark sector. Why do we assume dark matter is just one thing? The visible universe is not just one thing. It is made of quarks, electrons, neutrinos, photons, gluons, and Higgs bosons. It is a rich tapestry of particles. Why should the dark universe be monotonous? It is very likely that dark matter is a mixture. Perhaps it is 80% axions, 10% WIMPs, and 10% primordial black holes. Perhaps there are dark atoms that form dark stars, and those dark stars collapse into dark black holes. The dark matter we talk about might be an entire ecosystem of invisible entities, living their own lives, evolving their own structures, completely indifferent to the bright, noisy world of light we inhabit. The bullet cluster teaches us one final, humbling lesson. It shows us the resilience of the ghost. The normal matter, the gas, was stopped by the collision. It was shocked, heated, and stripped away from its galaxies. But the dark matter survived. It kept going. It carried the potential for future life with it. Because the dark matter provides the gravitational well, the gas will eventually cool down, fall back into the dark matter halos, and form new stars. The ghost is the guardian. It protects the structure of the universe from being destroyed by cosmic violence. Without dark matter, galaxy collisions would scatter gas into the void, ending star formation forever. But the ghost holds the cradle. It ensures that the universe can be reborn. As we ponder the violence of the bullet cluster and the silence of the primordial black holes, we must prepare ourselves for an even stranger journey. In the next chapter, we will look at the possibility that dark matter is not a substance at all, but a flaw in the fabric of reality. We will explore the idea of modified gravity. What if Einstein was wrong? What if gravity changes its rules when it gets very weak? We will look at the heretics of physics who dared to challenge the existence of dark matter entirely. We will see how they try to explain the rotation of galaxies without ghosts, and why the bullet cluster is their greatest nightmare. We will also touch on the dark fluid theory, which suggests dark matter and dark energy are two sides of the same coin, a single dark fluid that fills the cosmos. For now, hold on to the image of the bullet cluster, two giants smashing together, stripping their skin of gas, while their invisible souls continue on unhurt into the eternal dark. It is a reminder that what we see is fragile, but what we cannot see is eternal. The ghost is the true survivor. There is a seductive comfort in the idea of a law. A law is absolute. A law is eternal. When Isaac Newton sat beneath his apple tree and watched the fruit fall to the grass, he did not just see a piece of fruit. He saw a promise. He realized that the same invisible hand that pulled the apple to the earth also reached out across the void to hold the moon in its orbit. It was a unifying thought. It meant that the heavens were not made of magic. They were made of math. The force that governs the falling of a stone is the same force that governs the spinning of a galaxy. For 300 years, this belief has been the bedrock of physics. We believe in the universality of gravity. We believe that if you go to the edge of the universe, or into the center of a black hole, the rules of the game remain the same. Gravity is gravity. Mass attracts mass. The equation does not care where you are. But what if we are wrong? What if the ghost we have been chasing for decades, the dark matter that we believe makes up 85% of the matter in the universe, is not a thing, but a mistake? What if the universe is not filled with invisible particles, but rather our understanding of gravity is broken? This is the heresy of the modified Newtonian dynamics, or MOND. It is the rebel shout in the quiet library of astronomy. It asks a question that makes many scientists uncomfortable. Are we like the ancient astronomers who invented epicycles, complex invisible gears within gears, to explain the motion of the planets simply because they refuse to accept that the Earth orbits the Sun? Are we inventing invisible matter to save a broken theory? The story of this heresy begins in the early 1980s with an Israeli physicist named Mordechai Milgram. Milgram looked at the same rotation curves that Vera Rubin had studied. He saw the same impossibility. The stars at the edges of galaxies were moving too fast. But instead of imagining a halo of invisible matter to provide extra gravity, Milgram imagined a change in the law itself. He proposed that Newton's laws of gravity are not absolute. He suggested that they work perfectly well here on Earth and in the solar system, where gravity is strong, but in the deep, quiet outskirts of a galaxy, where the acceleration is incredibly small, 10 billion times weaker than the gravity you feel right now, the rules change. Milgram introduced a new constant of nature, a threshold of stillness called a zero. He argued that when the acceleration of a star drops below this tiny number, gravity stops fading away as quickly as Newton predicted. Instead of getting weaker with the square of the distance, it gets weaker much more slowly. It clings to the star. It holds on. In this view, the fast-moving stars at the galaxy's edge are not being held by a ghost. They are being held by a stronger, modified gravity that only wakes up in the silence of deep space. It is a radical idea. It suggests that the ghost is an illusion caused by our own ignorance of the true laws of nature. Before we explore how this heretical idea challenges the very foundations of cosmology, I am Walter, the explorer. I have been looking at our own community of curious minds, and I see that 73% of you who are traveling with us through these mysteries have not yet subscribed to the channel. If you find peace in these stories and want to support our mission to make the universe a little less lonely and a little more understandable, please take a moment to subscribe. It helps us tremendously to keep the lights on and the telescope focused on the unknown. The most unsettling thing about MOND is that it works. When we apply Milgram's simple formula to the rotation of spiral galaxies, it predicts their motion with eerie precision. It explains the Tully-Fisher relation, a famous law that links the brightness of a galaxy to its rotation speed more naturally than dark matter does. With dark matter, you have to fine-tune the amount of invisible halo to make the math work for every galaxy. You have to sprinkle just the right amount of dust to match the visible stars. It is messy. It feels like a fix. But with MOND, the rotation comes directly from the visible matter. You see the stars, you apply the modified law, and you get the rotation. One line of math, no ghosts, no invisible halos. It is elegant, sharp, and beautiful. And yet, the universe is rarely simple. While MOND wins the battle for the individual galaxies, it loses the war for the cosmos. When we look at the largest scales, the clusters of galaxies like the Coma cluster or the Bullet cluster, MOND fails. Even with the modified gravity, there is still missing mass. The clusters are moving too fast even for Milgram's law. To make MOND work for clusters, you still need to add some invisible matter, perhaps neutrinos. But if you have to add dark matter anyway, why modify gravity at all? The theory starts to look like a Frankenstein monster, a mix of new laws and old particles stitched together to fit the data. And then there is the cosmic microwave background, the afterglow of the Big Bang. The patterns in that ancient light fit the dark matter theory perfectly. MOND struggles to explain them. The ghost seems to be woven into the very beginning of time, in a way that a simple change in gravity cannot easily replicate. This standoff between dark matter and modified gravity is one of the great dramas of modern science. On one side, we have the particle hunters, who believe the universe is full of invisible stuff we haven't found yet. They have the bullet cluster and the Big Bang on their side. On the other side, we have the law modifiers, who believe our equations are incomplete. They have the elegant rotation of spiral galaxies on their side. It is a tension between adding new players to the game or changing the rules of the game. And in the middle of this tension, a third path has emerged, a path that is stranger and more poetic than either. What if dark matter is not a particle, and gravity is not wrong, but space itself is a physical substance? This is the theory of superfluid vacuum, or dark fluid. Imagine the universe not as empty space, but as a vast ocean of superfluid helium. A superfluid is a state of matter that exists near absolute zero. It has zero viscosity. It flows without friction. It can climb walls. It can exist in two states at once. The dark fluid theory suggests that the dark matter and dark energy are just different moods of this single cosmic substance. In this view, galaxies are like vortices or whirlpools spinning in this superfluid ocean. When the fluid is calm and still, it behaves like the dark energy that pushes the universe apart. But when it is stirred up by the rotation of a galaxy, it behaves like dark matter, creating a halo of pressure that holds the stars together. This theory tries to heal the rift. It says that on the scale of galaxies, the fluid creates a phonon, a sound wave of gravity that mimics Mond. It makes the gravity look modified. But on the scale of clusters, the fluid behaves like a particle, mimicking cold dark matter. It is a chameleon. It changes its skin depending on the environment. There is something deeply meditative about thinking of the universe as a fluid. It returns us to the ancient myths of the cosmic ocean, or the ether. It suggests that we are not isolated objects moving through a void, but patterns of energy moving through a continuous medium. We are waves on the water. The stars are the foam. The dark matter is the depth. It implies that space is not just a stage. It is an actor. It reacts. It flows. It has a temperature. It has a memory. Another visionary idea comes from the physicist Eric Verlinde, who proposes that gravity is not a fundamental force at all. He suggests that gravity is entropic. It is a side effect of the thermodynamics of the universe. Just as heat is not a thing, but the movement of atoms, gravity is not a thing, but the tendency of the universe to increase its disorder, its entropy. In Verlinde's view, dark matter is an illusion created by the way information is stored in the fabric of space. We think we see extra mass, but what we are really seeing is the memory of the space itself pushing back. We are seeing the elasticity of the vacuum. It is a concept that dissolves the ghost entirely. There is no dark matter particle. There is no modified law. There is only information, entropy, and the inevitable flow of time. These theories, Mond, dark fluid, entropic gravity, remind us that science is not a monolith of certainty. It is a living, breathing ecosystem of ideas. We observe the universe and we see anomalies. We see things that don't fit. The dark matter problem is the biggest anomaly of our time. It is a crack in the window through which we can glimpse a deeper truth. We are stuck between a ghost and a law. We are stuck between invisible particles that refuse to be found and mathematical equations that refuse to work everywhere. It is a beautiful mess. The pursuit of these alternative theories is driven by a philosophical razor. Occam's razor tells us that the simplest explanation is usually the correct one. But which is simpler? Is it simpler to invent a new particle that makes up 85% of the universe? a particle we have never seen? Or is it simpler to change an equation that was written down 300 years ago by a man who had never left Earth? The proponents of Mond argue that inventing invisible matter is a cheat. They say it is like seeing your house is cold and assuming there is an invisible ghost leaving the windows open, rather than accepting that your furnace is broken. The proponents of dark matter argue that changing the law of gravity is a desperate move that breaks the unity of physics. They say the furnace is fine. We just haven't found the open window yet. As we float in this uncertainty, we must appreciate the silence of the data. The universe does not shout its answers. It whispers them in the faint rotation of a dwarf galaxy, in the subtle bending of light around a cluster, in the cold patterns of the microwave background. We are trying to translate these whispers into human language, into mathematics. And perhaps, just perhaps, the translation is failing because the language we are using is too small. Perhaps the true theory of the dark universe requires a mathematics we have not yet invented, a concept we have not yet dreamed. The controversy of modified gravity teaches us humility. It teaches us that our most cherished laws, the laws we teach in school, the laws we use to navigate spacecraft, might be local approximations of a much grander, stranger truth. We might be living in a bubble of Newtonian space, unaware that out in the deep ocean of the cosmos, the rules are different. We are like ants who have figured out the physics of a sandcastle, unaware of the physics of the tide. In the next chapter, we will leave the heretics and the fluids behind and return to the hunt for the particle, but with a new twist. We will look at the possibility that dark matter is not dark at all, but transparent. We will explore the idea of mirror matter, a complete mirror universe occupying the same space as ours, with mirror stars, mirror planets, and maybe even mirror life. We will ask if the ghost is just a reflection of ourselves. We will also look at the future of the hunt, the new telescopes, the Euclid mission, and the Nancy Grace Roman telescope, which will map the dark universe with unprecedented clarity. We will see how we plan to turn the entire sky into a dark matter detector. For now, rest in the possibility that the laws of nature are not chains, but melodies. And like any melody, they can change. The song of gravity that plays near the sun might be different from the song that plays in the halo of a galaxy. We are listening to a symphony, and we have only just learned to hear the bass notes. The ghost might be the music itself. When you look into a mirror, you see a world that looks exactly like your own, but reversed. Your left hand becomes your right hand. The writing on your shirt flips backward. It is a perfect, silent imitation of reality. For most of human history, we have treated mirrors as simple tools, surfaces of polished metal or glass that reflect light. But in the strange and beautiful language of quantum physics, the concept of a mirror takes on a profound, almost haunting significance. Physicists have long been obsessed with symmetry. They believe that nature, at its deepest level, should be balanced. For every up, there should be a down. For every positive charge, a negative one. For every particle of matter, a particle of antimatter. This love of symmetry led to some of the greatest discoveries of the 20th century. But there is one symmetry that seems broken. In the 1950s, we discovered that the universe has a preference. When certain particles decay, they prefer to spin in one direction rather than the other. The universe, it seems, is left-handed. This violation of symmetry, called parity violation, disturbed the physicists who believed in a perfect, elegant cosmos. It felt like walking into a beautiful palace and noticing that one entire wing was missing. But what if the wing is not missing? What if it is just invisible? This question gave birth to one of the most imaginative and unsettling theories in the hunt for the ghost, the theory of mirror matter. The idea is simple but staggering. It suggests that for every particle in our standard universe, every proton, every neutron, every electron, every neutrino, there exists a mirror partner. These mirror particles would be identical to ours in mass and spin, but they would be right-handed, where ours are left-handed. They would interact with each other through their own mirror forces. Mirror atoms would bind together to form mirror molecules. Mirror dust would collapse to form mirror stars. Mirror planets would orbit those stars. And perhaps mirror life would evolve on those planets, looking up at a mirror sky. The reason we have not seen this mirror universe is that mirror particles do not interact with our light. They have their own mirror photons. To a mirror person, their sun would shine brightly with mirror light. But to us, it would be completely dark. We could stare directly at a mirror star and see nothing but empty space. Light from our sun would pass right through a mirror planet as if it were made of nothing. The two universes would share the same space, occupying the same volume, passing through each other like two ghosts in a hallway, completely unaware of each other's existence except for one thing: gravity. Gravity is the universal language. It is the only force that speaks to both sides. A mirror star would still have mass. It would still warp space-time. If a mirror star wandered into our galaxy, we would see its gravity pulling on our stars. We would see our stars orbiting an empty patch of sky. This theory of mirror matter offers a tantalizing explanation for dark matter. Perhaps the ghost is not some exotic new sludge or a swarm of tiny black holes. Perhaps it is just the other half of the universe, the missing reflection that restores the symmetry of nature. If this is true, then the dark matter halo that surrounds the Milky Way might not be a shapeless cloud. It might be a complex, structured place. It might contain mirror galaxies with spiral arms, mirror nebulas glowing with mirror light, and mirror solar systems. It is even possible that a mirror planet could be passing through our solar system right now, undetectable to our eyes, but exerting a tiny, subtle gravitational tug on our planets. It is a thought that makes the silence of the night sky feel crowded. We might be walking through a mirror city every day without ever knowing it. This leads us to a broader realization. We have been assuming that the dark sector is simple, but why should it be? Our visible universe is a riot of complexity. We have the periodic table of elements with carbon, oxygen, gold, and uranium. We have forces that build mountains and forces that burn in stars. Why should the dark universe be boring? In recent years, scientists have begun to model complex dark matter, or atomic dark matter. They propose that a fraction of the dark matter, maybe 5 or 10%, can interact with itself. It can cool down. It can radiate dark energy, not the accelerating kind, but simply energy in the dark sector. If dark matter can cool, it can do something the standard cold dark matter cannot. It can collapse into a flat disk. Lisa Randall, a theoretical physicist at Harvard, has proposed that there might be a dark disk embedded inside the visible disk of the Milky Way. While the vast halo of cold, dark matter stays puffed up in a sphere, this interacting dark matter would settle down into a thin, dense pancake of dark material, right where the stars are. This dark disk would be invisible, but powerful. As our sun orbits the galaxy, It bobs up and down, passing through the galactic plane every 30 million years or so. Randall has suggested a poetic and terrifying connection. Every time the solar system passes through this dense, dark disk, the extra gravity might disturb the comets in the Oort cloud, sending them raining down into the inner solar system. She has looked at the timing of mass extinctions on Earth, including the one that killed the dinosaurs, and found a rough pattern that matches this bobbing motion. It is a speculative idea, but it connects the death of the dinosaurs to the hidden architecture of the galaxy. It suggests that a disk of shadow matter, invisible to the eye, might have reached out and altered the destiny of life on Earth. But the complexity of the dark sector might go even further. In the very early universe, long before the first galaxies formed, the dark matter might have played a different role. It might have powered the first stars. We call these hypothetical objects dark stars. They are not made entirely of dark matter, but they are powered by it. In the standard picture, the first stars, population 3 stars, were powered by nuclear fusion, burning hydrogen into helium. But if dark matter is made of WIMPs, and if WIMPs are their own antiparticles, then when two WIMPs meet, they annihilate. They turn into pure energy. In the dense clouds of the early universe, dark matter would have been concentrated in the center of the forming stars. The annihilation of these particles would produce a heat source that could support the star against gravity without the need for fusion. These dark stars would be monstrous because they don't need to be hot enough for fusion. They could grow to be millions of times more massive than the sun. They would be giants, puffy and cool, glowing not with visible light, but with infrared heat. They would be fuzzy blobs of warm gas, light years across, powered by the burning of the ghost within. If they existed, they would have been the first lanterns in the cosmic dark ages. They would have lived for millions of years, eventually collapsing to form the supermassive black holes we see today. The James Webb Space Telescope, with its infrared eyes, is currently hunting for these ancient giants. If we find one, it would be the first direct sign that dark matter is not just a gravitational anchor, but a fuel. So how do we find the truth? We cannot touch the mirror world. We cannot see the dark disk. We can only map the shadows. And to do that, we are building the greatest cartographic instruments in human history. We are entering the golden age of dark matter observation. The hunt is moving from the underground mines to the high vacuum of space. In July of 2023, the European Space Agency launched a telescope named Euclid. Euclid is not looking for beautiful pictures of nebulas to put on screensavers. It is a surveyor. It is looking at the shapes of billions of galaxies, covering more than a third of the entire sky. It is looking for weak gravitational lensing. As we discussed with the bullet cluster, gravity bends light, but for most galaxies this bending is tiny. It doesn't create arcs or rings. It just slightly distorts the shape of the background galaxy. It makes a round galaxy look a little oval. This effect, called cosmic shear, is invisible to the eye. But by measuring the shapes of millions of galaxies and averaging the data, Euclid can detect this tiny distortion. It can create a 3D map of the dark matter distribution across 10 billion years of cosmic history. Euclid is drawing the skeleton of the universe. It is showing us where the bones are buried. Following Euclid, NASA will launch the Nancy Grace Roman Space Telescope. This instrument is a powerhouse. It has a field of view 100 times larger than the Hubble Space Telescope. Imagine trying to map a forest by looking through a drinking straw. That was Hubble. Roman is like opening a panoramic window. It will survey the sky with the same sharpness as Hubble, but with vastly more speed. It will look for the tiny brightenings of stars caused by primordial black holes. It will map the distribution of galaxies with unprecedented precision. It will hunt for the clumpiness of dark matter. If dark matter is warm or fuzzy, like axions, it will not form small clumps. If it is cold, like WIMPs, it will. Roman will read the texture of the ghost. And on the ground, in the high deserts of Chile, a new eye is opening. The Vera C. Rubin Observatory is building the legacy survey of space and time. This telescope is a beast. It has the largest digital camera ever built for astronomy, the size of a small car. Every few nights, it will photograph the entire visible sky. Over 10 years, it will create a movie of the universe. It will see things that move, things that flicker, and things that change. It will track the orbits of billions of stars, looking for the subtle streams and ripples caused by dark matter halos. It will give us the most complete census of the cosmos ever attempted. These machines, Euclid, Roman, Rubin, are the cathedrals of our time. They are built by thousands of people from dozens of nations, united by a single abstract goal: to understand the 95% of the universe that is hiding from us. There is something deeply moving about this effort. We are spending billions of dollars and millions of hours not to conquer a new land, not to mine a new resource, but simply to know. We are driven by the need to understand the room we are standing in. As these new eyes open, we must be prepared for surprises. The history of astronomy is a history of being wrong, or at least of being only partially right. We might find that the dark sector is far stranger than mirror matter or dark stars. We might find that the universe is teeming with structures we have no names for yet. We might find that the ghost is actually a choir, a symphony of different particles and forces playing a music we are just beginning to hear. This search connects us to the ancient explorers who sailed across the oceans of Earth. They had crude maps with monsters drawn in the margins. They navigated by the stars, trusting that there was land on the other side of the silence. We are sailing the ocean of the night. Our maps are mathematical. Our monsters are black holes. But the spirit is the same. We are pushing the boundary of the known world. In the next chapter, we will turn our attention to the other side of the dark coin. If dark matter is the force that holds the universe together, then dark energy is the force that is tearing it apart. We will explore the discovery that shook the foundations of science in 1998. The universe is not just expanding, it is accelerating. We will look at the Big Rip, a terrifying future where dark energy becomes so strong it tears apart galaxies, then stars, then atoms, and finally, time itself. We will ask if dark matter and dark energy are enemies, fighting a cosmic war for the fate of the universe. We will stand at the edge of the ultimate horizon and look into the abyss of the future. For now, look into the mirror one more time. Look at your own eyes. Realize that the atoms in your reflection are visible, but the gravity of your body is real. Somewhere in the deep geometry of a space, there might be a reflection that has no face, a shadow that has no light, a ghost that is waiting to be found. The universe is a hall of mirrors, and we are just beginning to learn how to look. We often think of nothing as a lack of something. If you take a box and pump out all the air, remove every single atom of dust, shield it from every photon of light, and cool it to absolute zero, you might think you have created a perfect void. You might think the box is empty, but you would be wrong. In the strange and counterintuitive accounting of the cosmos, empty space is not zero. It is not a vacuum in the sense of absence. It is a plenum in the sense of potential. It has a weight. It has a cost. And, most terrifying of all, it has a push. For most of the 20th century, astronomers believed that the universe was a simple story of expansion and gravity. We knew the universe began with a bang, a sudden, violent expansion that sent matter flying outward in all directions. We assumed that gravity, the attractive force of all that matter pulling on itself, would act as a brake. We looked at the stars, the galaxies, and the vast halos of dark matter, and we said, "This is the anchor." We believed that eventually the expansion would slow down. The only question was whether it would stop completely and collapse back into a big crunch, or if it would just coast forever, slowing down, but never quite stopping, like a car running out of gas on a long, flat highway. It was a comforting, logical picture. It felt like a ball thrown into the air. It goes up, gravity pulls it, it slows down. But in 1998, two teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, looked at the sky and broke physics. They were using Type 1a supernovae as standard candles to measure the expansion rate of the universe. These are exploding white dwarf stars that always burn with the exact same brightness, allowing us to measure their distance with incredible precision. The astronomers expected to see that the distant supernovae were brighter than a constant expansion would predict, meaning they were closer, meaning the universe was slowing down. They analyzed the light of dozens of dying stars, billions of light years away. They checked their numbers, they checked their telescopes, they checked their software, and then they looked at each other in stunned silence. The supernovae were too faint. They were much farther away than they should have been. The universe was not slowing down. It was speeding up. Imagine throwing a set of keys into the air. You watch them rise, expecting them to peak and fall back into your hand. But instead, halfway up, they suddenly accelerate. They shoot upward towards the clouds, moving faster and faster, defying the gravity of the earth. That is what the universe is doing. Some mysterious, invisible force is pushing the galaxies apart, overcoming the gravitational pull of all the stars and all the dark matter combined. We call this force dark energy, and it is not a small correction. It is the dominant power in the cosmos. Before we grapple with the existential vertigo of an accelerating universe, I am Walter, the explorer. I look at our growing community of stargazers, and I see that 73% of you are traveling with us without a ticket. You haven't subscribed yet. If these journeys into the dark help you find a moment of wonder in your day, please subscribe. It supports our work and ensures that we can keep exploring the edges of the known together. The discovery of dark energy rewrote the recipe of the universe overnight. We realized that everything we had been studying, the protons, the electrons, the neutrinos, the WIMPs, the axions, the black holes, was just the debris floating in a vast ocean of energy. The current census is humbling. About 68% of the universe is dark energy. 27% is dark matter, and less than 5% is normal matter. We are the foam on the waves. The dark matter is the water, but dark energy is the ocean floor spreading beneath us. But what is dark energy? Unlike dark matter, which clumps together and forms halos, dark energy seems to be perfectly smooth. It does not cluster in galaxies. It does not pile up in the center of the universe. It is a property of space itself. This leads us to the cosmological constant, an idea originally proposed by Albert Einstein. Einstein added a term to his equations of general relativity, a fudge factor, to keep the universe static, to stop gravity from crushing it. When Edwin Hubble discovered the universe was expanding, Einstein called this constant his biggest blunder. But it turns out he was right all along, just for the wrong reason. The cosmological constant represents the energy density of the vacuum. It says that empty space has an intrinsic energy. And here is the kicker. As the universe expands, it creates more space. More space means more dark energy. More dark energy means more push. More push means faster expansion, which creates even more space. It is a runaway feedback loop, a self-feeding engine of nothingness that is tearing the cosmos apart. This creates a cosmic war between the two dark titans. On one side, we have dark matter. It is the builder. It is the force of gravity pulling things together, creating structure, weaving the cosmic web, birthing galaxies, and nurturing stars. It tries to hold the universe in a warm embrace. On the other side, we have dark energy. It is the destroyer. It is the force of anti-gravity, pushing things apart, stretching the voids, dissolving the web, and isolating galaxies. For the first few billion years of the universe, dark matter was winning. The universe was smaller, and the density of matter was high. Gravity dominated. This was the era when the great clusters formed. But as the universe expanded, the density of matter dropped. The galaxies got farther apart. The gravity got weaker, but the density of dark energy stayed the same. It is constant. About 5 billion years ago, the scales tipped. The density of matter dropped below the density of dark energy. The builder lost its grip. The destroyer took the wheel. Since then, the universe has been in a phase of runaway acceleration. We are living in the era of dark energy. This timing leads to the coincidence problem. Why now? Why do we happen to live in the brief moment in cosmic history where dark matter and dark energy are roughly comparable? If we had evolved 10 billion years earlier, dark energy would have been negligible, a tiny footnote in the laws of physics. If we had evolved 10 billion years later, dark energy would be so dominant that we wouldn't even be able to see other galaxies. We live in a privileged time. We live in the only time when we can see the battle happening. We can look out and see the structure built by dark matter, and we can measure the acceleration driven by dark energy. We are standing on the ridge between the past and the future, witnessing the turning of the tide. There are other theories, of course. Just as we asked if dark matter could be something else, we must ask if dark energy is really just the energy of empty space. There is a theory called quintessence, named after the fifth element of the ancient Greeks. Quintessence suggests that dark energy is not a constant, but a dynamic field, like a fluid that fills the universe, that can change over time. It can evolve. It can get stronger or weaker. If it gets weaker, the universe might eventually slow down again. If it gets stronger, it leads to a terrifying possibility called the phantom energy scenario. In a phantom energy universe, the force of repulsion grows stronger as the universe expands. It doesn't just push galaxies apart. It starts to push stars apart within galaxies. Then it pushes planets away from their stars. Then it tears planets apart. Then it rips molecules apart. And finally, in the last fraction of a second of the universe, it rips atoms apart. This is the Big Rip. It is a violent, shredding end to all structure. It is the ultimate victory of the void over the substance. But let us step back from the apocalypse and consider the philosophical weight of this discovery. We are made of atoms that want to cling together. Our biology is based on connection, molecules binding to receptors, cells binding to tissues, people binding to communities. We are creatures of gravity. We understand attraction. We understand the need to be close. But we live in a universe that is fundamentally defined by repulsion. The dominant force in our reality is a force that wants to be alone. It wants to create distance. It is a lonely force. This duality, the tension between the gravity that binds and the energy that separates, is the central conflict of the cosmos. And dark matter is the hero of this story. It is the only reason we are here to think about it. Without the extra gravity of the dark matter halos, the dark energy would have won the war billions of years ago. It would have ripped the primordial gas clouds apart before they could form stars. It would have diluted the universe so fast that galaxies would be impossible. We exist because the ghost held on tight. The dark matter halo of the Milky Way is a fortress. It is a gravity well deep enough to protect us from the expanding void. Inside this halo, gravity is still king. The solar system is not expanding. Your body is not expanding. The galaxy is not expanding. We are safe in the harbor while the storm rages out at sea, but the storm is getting stronger. And as we look at the distant universe with our new telescopes, Euclid, Roman, Rubin, we are trying to measure the equation of state of dark energy. We are trying to find out if it is a constant or if it is changing. We are looking for the W parameter. If W is exactly -1, then it is a cosmological constant, and the universe will end in a big freeze, expanding forever until the stars burn out. If W is less than -1, we face the big rip. If W is greater than -1, there is hope for a different future. The measurement of this parameter is one of the most difficult tasks in science. It requires measuring the shapes of millions of galaxies and the distances to thousands of supernovae with an accuracy of less than 1%. It requires understanding the dust, the gas, and the intrinsic variations of stars. It is a task that pushes human ingenuity to its breaking point. But we do it because we need to know the ending of the story. We need to know if the ghost that holds us is strong enough to last forever, or if the void will eventually swallow everything. In the next chapter, we will walk through the big freeze. We will simulate the future of a universe dominated by dark energy. We will watch as the other galaxies disappear from our sky, carried away by the faster-than-light expansion of space. We will stand on a future Earth orbiting a dying red sun and look up at a sky that is almost perfectly black, save for the few remaining stars of our own merged galaxy. We will explore the concept of the cosmic horizon, the limit of our knowledge. We will see how dark energy is slowly erasing the history of the universe, making it impossible for future civilizations to know that there was ever a Big Bang. We will confront the ultimate loneliness of the dark universe. But for now, take comfort in the gravity. Feel the weight of your body. That weight is a victory. It is a sign that in this small corner of the vast accelerating cosmos, the builder is still winning. The ghost is still holding you. The darkness has not yet conquered the light. In the profound quiet of the far future, the universe will undergo its most melancholy transformation. For billions of years, we have lived in a cosmos defined by connection. We have watched galaxies collide, stars merge, and the cosmic web tighten its grip. But the acceleration of space, driven by the relentless push of dark energy, is slowly beginning to erase the work of the ghost. If dark energy remains constant, as Einstein's cosmological constant suggests, we are heading toward a fate called the Big Freeze. It is a future of ultimate isolation, where the vast structures built by dark matter are slowly dismantled by the stretching of the void itself. Imagine an astronomer living on a planet orbiting a distant star. 100 billion years from now, they look up at the night sky, expecting to see the trillions of galaxies that we see today. But they see nothing. One by one, the distant galaxy clusters have been carried away by the expansion of space, moving faster than the speed of light can travel back to us. They have vanished behind the cosmic horizon, a boundary beyond which no information can ever return. To this future observer, the universe will seem to consist of only their local, merged galaxy, floating in an absolute, terrifying blackness. The evidence of the Big Bang, the cosmic microwave background, and the existence of other galaxies will be gone forever. They will live in a universe that has forgotten its own history. Within our own local neighborhood, the battle between the light and the dark will reach its final stage. In about 5 billion years, our sun will swell into a red giant, consuming the inner planets and ending the story of Earth. The Milky Way and Andromeda, once separate island universes, will have completed their long gravitational dance, merging into a single, massive, elliptical galaxy. This new galaxy, often called Milkomeda, will be the last fortress against the dark energy. But it will be a fortress of dying embers. The gas supply that feeds the birth of new stars will eventually be exhausted, used up by previous generations, or pushed away by the accelerating expansion. The era of star formation, the brief flowering of the cosmos that allowed for the emergence of life, will come to an end. One by one, the 100 trillion stars will begin to wink out. The massive blue stars will go first, dying in spectacular supernovae that light up the darkness for one last time. Then the yellow stars, like our sun, will fade into white dwarfs. Finally, only the tiny red dwarfs will remain, burning their fuel with a desperate slowness for trillions of years. But even they have a limit. Eventually the last red dwarf will exhaust its hydrogen and go dark. The galaxy will become a graveyard of cold stellar remnants, white dwarfs, neutron stars, and black holes drifting in an eternal night. Even the ghost itself, the dark matter that built the house, will not be immune to the passage of time. If dark matter is made of particles like the WIMP or the axion, they may eventually decay or annihilate. If it is made of primordial black holes, they will slowly evaporate through Hawking radiation. Over timescales so vast they beggar the human imagination, a Google years, a one followed by 100 zeros, even the supermassive black hole at the heart of our galaxy will dissolve into radiation. The universe will reach a state of maximum entropy, where all energy is spread perfectly thin, and no further work can be done. This is the heat death of the universe, the final silence, where the ghost and the light both vanish into the void. Before we face this ultimate horizon, I am Walter, the explorer. We are approaching the end of our journey through the dark, and I see that 73% of you who have stayed with me through these deep time scales have not yet subscribed. If these explorations of the cosmic future help you appreciate the preciousness of the present moment, please consider subscribing. It is the best way to ensure that we can continue to wonder at the universe together before the lights go out. The Big Freeze might seem like a story of despair, but there is a strange, cold beauty in it. It reminds us that we live in the golden age of the cosmos. We exist in that narrow window of time when the universe is old enough to have produced heavy elements and life. but young enough that the stars still shine and the distant galaxies are still visible. We are the part of the universe that has woken up just in time to see the show. We can see the cosmic web, we can measure the dark matter, and we can feel the push of dark energy. We are the witnesses of a magnificent, fleeting transition. This realization transforms our understanding of the ghost. Dark matter was the architect that allowed this brief moment of complexity to exist. It provided the stability that allowed stars to burn and planets to form. It fought against the acceleration of space for billions of years, holding the cradle tight. If the universe is a symphony, dark matter provided the steady, deep bass notes that gave the melody of life its structure. Even if that symphony eventually fades into silence, the fact that it played at all is a miracle. As the cosmic horizon closes in and the expansion of space carries the rest of the universe away, we are left with a final, haunting question. Why? Why is there something rather than nothing? Why did the dark matter gather the light, only for the dark energy to tear it away? Science may never be able to answer the why, but it has given us the how. It has shown us that we are not separate from this process. We are the star stuff that has learned to wonder about the dark. The journey of the ghost ends in the same place it began, in the unknown. We started this exploration by asking what dark matter is made of, and we have traveled from the quantum foam to the edges of eternity. We have looked at WIMPs, axions, black holes, and modified gravity. We have seen the bullet cluster and the cosmic web, and while we still do not have a single particle in a jar, we have something more valuable, a deeper connection to the mystery. As you prepare to return to your daily life, take one last look at the night sky. The darkness you see is not empty. It is full of the invisible halos that hold the stars in their place. It is humming with the dark energy that is shaping the future. You are standing on a small, bright island in a vast, dark ocean. But that ocean is your home. You are made of its elements, governed by its laws, and part of its destiny. The ghost is not an intruder. It is your ancestor. In the final stage of our journey, we must recognize that the search for dark matter is more than a quest for a missing particle. It is the ultimate expression of human consciousness reaching out to touch the face of the infinite. We have traveled from the microscopic vibrations of quantum fields to the silent, stretching voids of a future shaped by dark energy. Through it all, the ghost has been our constant companion, the invisible architect that gathered the primordial gas, built the cosmic web, and provided the gravitational sanctuary where our sun and planet could safely reside. We have seen that we are rare creatures. The atoms that make up our bodies, the carbon, the iron, the oxygen, are exotic anomalies in a universe that prefers to be dark, cold, and transparent. Yet, this realization does not make us insignificant. Instead, it highlights the remarkable miracle of our existence. We are the star stuff that has developed the ability to observe, measure, and wonder about the 95% of reality that cannot see us back. As we look toward the future, we see the tools of the next generation, telescopes like Euclid, Roman, and the Rubin Observatory, preparing to pull back the veil. They will map the shadows with a precision our ancestors could never have imagined, turning the entire night sky into a laboratory for the dark sector. We may finally catch the whisper of the axion, the jolt of a primordial black hole, or the faint signal of a mirror universe. Or perhaps we will find that our laws of gravity were merely a local melody in a much grander symphony. Whatever the answer, the journey itself is what defines us. We are part of a tradition that stretches from the first humans who looked at the Milky Way and saw a river of spirits, to the modern explorers who see a halo of invisible mass. We are a bridge between the light and the dark, a momentary flicker of awareness in a vast, ancient, and beautiful cosmos. The biggest galaxy ever discovered, IC 1101, stands as a monument to this mystery, 100 trillion stars held in the grip of a ghost that will outlast the light itself. It reminds us that, while our lives are brief, our reach is infinite. We can touch the edge of time with our minds, and we can find peace in the realization that we are held, nurtured, and connected by forces we are only just beginning to name. Thank you for joining me, Walter, the explorer, on this voyage into the heart of the unknown. If this exploration of the quantum ghost and the dark universe has helped you see the night sky as a full and vibrant home, remember to carry that wonder with you. The universe is deep, the mysteries are many, and the journey is just beginning. Keep looking up, keep asking questions, and never stop wondering at the beautiful, silent shadows that hold the stars.